The final concentration unit we want to talk about for chapter 11 is molality. So molality has a symbol of a lowercase m that's script. So it's italics. So I can't really draw italics. So how I represent this is like a cursive M. So I do 1, 2, 3. It's about as good as my actual handwriting is, but I'm going to do 3 swoops on an M. That's for an italics M, but it is lowercase for molality. You'll note this word is very similar to molarity. We just have the difference is all in that L. So we do want to be careful sometimes when we're reading problems. We don't want to be careful parsing out, is this molality or is it molarity? So molality, very similar to molarity in that the numerator is moles of solute. So moles of solute is the same, but on the denominator is mass of solvent in kilograms. So just like molarity, that the bottom, the volume had to be in liters, here the mass has to be in kilograms. Okay, so that's one of the things. The other thing that is unique about molality is that the denominator value is not an amount of solution, it is an amount of solvent. Okay, so it is moles of solute per mass of solvent. Molality is the only concentration unit where the bottom is not solution amount, it is solvent amount. So why do we need molality? Well, molality has one very important property, and that is that it does not change with temperature. When you change the temperature of something, water, a piece of metal, gas, the volume changes. So in some cases, it changes a lot. Gas volumes change a lot when you change the temperature, but even the volume of water does change a little bit. And so if the volume changes with temperature, anything that depends on temperature also changes. And so molarity, for example, changes as you change temperature. Okay, and we generally don't want that to happen. If we're looking at, say, a property that changes with temperature, we don't want to be using a concentration unit to describe that property change if the concentration unit is changing with temperature. So we use molality in situations where the temperature is going to be changing. So freezing point depression, boiling point elevation, we are purposefully changing the temperature. We want our concentration unit description to be the same. The other thing that is useful about molality is you will note it is per mass of solvent. That per solvent is basically means this unit was invented to describe colligative properties. Colligative properties are all about changes relative to the solvent properties. That's what this is all about. So how can we, it's a temperature independent one and it's designed for colligative properties. We basically invented molality as a concentration unit in order to describe boiling point elevation and freezing point depression. So that really is the only application where you commonly see molality, but it's the only thing you can use for that application. So let's see an example. 35 grams of formaldehyde is dissolved in 250 milliliters of water. What is the molality of the resulting solution? So this is like we've seen with all the other concentration units. We want to be able to form a solution and then characterize the concentration. I dissolved some amount of solute in some amount of solvent. What is the molality or whatever the concentration is of the solution? All right, we want to know the molality of our solution when 35 grams of formaldehyde is dissolved in 250 milliliters of water. So just like we have seen so far, molality is a concentration unit. We want to recognize that that has an equation associated with it, that molality is going to be moles of solute divided by kilogram of solvent. So importantly, it is kilograms of solvent. So we want to, in this case, we need to figure out what's our solute and what's our solvent. And both of our components are going to be just the amount of the solute in the solvent. There's no solution overall. So because 35 grams of formaldehyde is dissolved in water, what that tells us is that our solute is going to be the CH2O and our solvent is going to be H2O. So do I have moles of solute, CH2O? No, I do not. I have grams of it. But grams can get turned into moles using molar mass. Do I have kilograms of water? No, I have 25 milliliters of water. So I have amounts of everything I want. They're just not in the right units. So I just need to do some conversions. So I have 35 grams, in this case, of CH2O, and I want to turn that into moles. So the molar mass of formaldehyde is 30.03 grams CH2O for every 1 mole of CH2O, giving me 1.2 moles of CH2O. That's good. I've taken my grams of solute and turned it into moles of solute. I also need to get my kilograms of solvent. Right now, I have 250 milliliters of water. So I have a couple issues. One, milliliters is not the right unit for kilogram. It's also not even the right type of unit. I'm currently in a volume unit, and I need a mass unit of kilograms. So in order to get that, I need to convert 1 milliliter is 1 gram of water. This relationship is that 1 gram per milliliter is the density of water. So I use density to go back and forth between grams and milliliters. For the case of water, it's, generally if you make this, you kind of get away with it because it's 1-to-1, so numerically, it is just 250 grams of water. But we do be mindful that this is using density to go back and forth between volume and mass. It's very common in the world of concentration, especially because we're dealing with kilograms of solvent in the case of molality. Mass percent also is dealing with mass of solution. So it's very common that you use density in this context to go back and forth. So we're in mass. We're not quite done. 250 grams of water needs to be converted into kilograms. 1,000 grams per kilogram. 0.25 kilograms. Just like we've seen with molarity before, it's not just, it wasn't in the case of molarity, it's not liters of solution, or it's not volume of solution, it's liters of solution. This isn't mass of solvent, it's kilograms of solvent. So we always want to make sure that our solvent is in units of kilogram. We can take those two values, put them together. The molality is 1.2 moles of CH2O divided by 0.25 kilograms of water. One of the things that's unique about molality is that you have a substance, a specific formula in the top and the bottom, the solute and the solvent. We divide those out, we get 4.8 as the number, and moles divided by kilo, we get moles CH2O divided by kilograms of water. This whole thing, moles per kilogram, is called molality. And so normally how we would write this is we would say it's 4.8 molal CH2O. And so just like we've seen with all our previous concentration units, by knowing what we put in, the amounts of our solvent and solute, we want to be able to characterize our solution based on concentration. Like we saw previously, a lot of times our input units need to be converted into the particular units required for that concentration unit. But then once we do that conversion, we can put them together using the equation that defines that concentration unit. Participation 9.9, question 2. What mass of water should be used to dissolve 17 grams NH3 in order to create a 2.5 molal solution? Helpful molar masses, NH3 is 17.04 grams per mole, and H2O is 18.02 grams per mole. This is the second question on participation 9-9 due Tuesday, September 9th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, what mass of water should be used to dissolve 17 grams of NH3 in order to create a 2.5 molal solution? And I'm giving you molar masses there. You are not, in a problem like this, I'm going to give you molar masses. I'm not saying you need to use all of the molar masses, but any molar mass you do need is provided. Generally, they're all provided. You might have to use one, but you don't, at this point in time, I'm not going to be asking you to figure out molar masses. That's a chemistry 1 thing. So I'm just going to give molar masses. I'm going to give all of them for all substances in any problem. And then you need to be able to pick which ones are appropriate to use. That is part of this class. So molality is really weird. It's this really kind of odd, off concentration unit. So the question is, why and when would we ever need to use it? And the most important part about molality is that the denominator is the kilograms of solvent. That's one of the things that makes it weird. It makes it kind of hard it makes it very different from other concentration units and kind of hard to work with. But importantly, because it's one of the things about it being different from all concentration units, the fact that it's a mass of solvent means that the denominator does not change with temperature. Volume of solution changes with temperature. Things expand and contract with temperature. So molality does not change with temperature. And that's really important because it means you have to use molality for properties that change with temperature. So one property that changes with temperature is the fact that solutions have higher boiling points than pure solvents. So the boiling point of a solution is higher than the boiling point of the pure solvent. Same idea as vapor pressure. So we need to use molality here because of its temperature independence. Similarly, on the other side, solutions have lower freezing points. The solute molecules get in the way, blocking basically the formation of, say, a crystal structure of your molecular solid. So the solute molecules are in the way. It dissolves. They're blocking. So then you have to get to lower temperatures to cause freezing. And so, we use this practically for icing roads in colder climates where freezes happen more regularly or every year, and snow and stuff like that. And so, these are properties where temperature is changing, and you're looking at the property of a solution. So the concentration you're using to characterize that solution, you don't want to be changing over the course of the process. So you can't use molarity here. So when you're dealing with this freezing point depression or boiling point elevation, you have to use molality. It's weird, yeah, but we do need to use molality in those contexts. It is the fraction of moles of one substance to all. All right, we had another participation question in this video. And I think, oh, I missed it. We're over halfway. Last video was halfway. We are over halfway on the backstretch. See if we find some more questions. See you in the last few videos.